If you are watching this video, then you are enrolled in my Chemistry 216 course, and you've actually read and opened and read the email I sent that had Quiz 0. I call it Quiz 0 because technically it does not count for anything, but it will impact you if you don't do it. Because Chemistry 216, Inorganic Chemistry, is going to draw from all of the topics that you covered in general chemistry, directly or indirectly. There are a few things such as kinetics and thermodynamics that we won't get into in a great deal in 216. We'll cover it to a certain extent. However, what I can absolutely guarantee you is day one we will be talking about quantum mechanics. And the reason this is an absolute certainty, which is ironic, hopefully you'll understand that in reviewing quantum mechanics, is because chemical bonding is much more sophisticated than you know based on general chemistry. In general chemistry, I'm basically diving into the meat and potatoes. In general chemistry, you learned the Lewis dot structures. However, we're going to find in this course that there are many situations where chemical bonding cannot be explained using a Lewis dot structure. Just doesn't work. It gives you nonsensical answers. It gives you results that do not reflect reality. To understand those situations, the real world, we have to bring in more sophisticated aspects of chemical bonding. All of that is grounded in quantum mechanics. So if you are shaky on the beginning of quantum mechanics, which would have been in General Chemistry 1, Chemistry 111, that's going to be a problem. So Quiz 0 will help get you up to speed by finding all your flaws, your problems. In other words, if you can't answer some of these questions like that, you need to go back to your Chemistry 111 notes. You need to go back to your textbook. I've sent a link with the open source textbook. If you have your old quizzes and exams from general chemistry, now is a good time to go over them. So in the very first problem, where I ask about the which quantum number sets are allowed and which are not. So which quantum sets are not allowed. The most obvious question is, well, what do I mean by quantum numbers and quantum number sets? So right now, I am not going to go through all of these problems and give you the answer. I will post an answer key later, but now I want to give you a flavor of what you should know. Hopefully everything will sound familiar. So in this first problem, I give you a several sets of quantum numbers, and I'm asking you which is not allowed. The first and most important thing is, well, what do I mean by quantum numbers, set of quantum numbers? So if we recall, there is the quantum number n, which is referred to as, and I am intentionally not going to tell you this information. You have to go look it up. I will do a review on the first day of class, but I want you to have to go back to your textbook and dig some of this up. The allowed values for n are 1, 2, 3, all the way to infinity. But what other restrictions are there? Well, you notice there's no 0, and there are no fractions. N must be an integer, a whole number. Okay? L, our next quantum number. Okay? The values of n dictate what are allowed for L. 0 through n minus 1. If n is 1, L can only be 0. If n equals 2, L can be 0 and 1. So L will have multiple values, potentially multiple values. As I am writing out these quantum mechanical variables, you can think of them as variables, what should you be relating them back to? I'll give you a moment to think about that before I finish. What do these physically represent? M sub L is equal to negative L through 0 to positive L. The first three quantum numbers, these are used to define the atomic orbitals for a given element, right? Everything I'm saying right now should be very familiar. That's why I'm leaving out, for example, this is the principal quantum number, but you knew that, of course. And what does it physically get us to? The spoiler is, of course, this is leading to the periodic table, okay? So you need to think of the quantum numbers in terms of the periodic table. Mendeleev derived the modern periodic table, or what's very close to the modern periodic table, in the 1870s. Around the 1930s, Schrödinger worked out quantum mechanics. So the periodic table, as we know it, has been around for quite some time. However, in Schrödinger's work, what he did was he created a mathematical basis for the periodic table, whereas Mendeleev did it purely based on empirical knowledge. In other words, the elements, their physical properties. Now, these are the first three quantum numbers. There's one more quantum number that we need, and that is m sub s. But m sub s can have two values, positive 1/2 or negative 1/2. What am I talking about with m sub s? What is this positive 1/2 and negative 1/2 defining? What property of what species? Okay? Again, if you don't know that, like that, you need to go back and review your notes inside and out with the quantum numbers. You need to know all the quantum numbers and what they represent and how we tie that back to the periodic table. So now with these four quantum numbers, in the homework I gave you sets of four quantum numbers, and you have to tell me which values are not allowed, and going from there. So I'll go through a few more of these problems. I'll edit this video, but this is not meant to be punitive, this homework 0 that I'm throwing at you. This is meant to basically give you a very cold splash of water to the face, which sounds punitive, to help you when the course starts. Because if you have not started reviewing quantum mechanics, chemical bonding, before the course starts, when week 1 gets here, you're going to be behind, because you're going to have not just my class, but other classes to deal with, right? So you can save yourself some grief in the first few weeks of class by reviewing General Chemistry 1, especially for those of you who might have taken General Chemistry 2 years ago. In other words, if you've already taken organic chemistry or beyond, it might be more than a year from when you took Gen Chem 1. So it's very easy to forget the fundamentals. I am speaking as a student. When I was your age taking inorganic chemistry, I made all these mistakes of not going back and getting the fundamentals of quantum mechanics and chemical bonding solid. That way, when you learn the new material, you can move forward in a very smooth manner. In other words, if you don't understand Lewis dot structures, for example, When I introduced more advanced aspects of chemical bonding, that is going to be a problem. Okay? So I'll go through, again, a few more of these, and I will be adding more videos going forward. But I'm intentionally leaving some stuff out. Like, for example, I'm not answering the question. I'm just giving you this basic framework because you need to go get your notes, get a textbook, and go through this material yourself. So problem 2, which of the following elements is paramagnetic? And there is more than one possible answer. Well, what's the most obvious question here? Paramagnetic, what does that mean? What other choice is there besides paramagnetic? The next question, problem 3, asks you to write the ground state electron configuration for the following species. A big hint is, well, if you want to know is a chemical species paramagnetic or diamagnetic, you need to write the electron configuration. In the case of an element, it's going to be the ground state electron configuration. For molecules, it will be their Lewis dot structure, or later on we'll see the molecular orbital theory, a molecular orbital diagram as we get into MO theory. So, paramagnetic versus diamagnetic. And again, I am going through this in a very cursory way, just to refresh your memory, but you definitely want to go back and read through this in quantum mechanics. Paramagnetic means that you have a chemical species that has one or more unpaired electrons. A paramagnetic species is strongly attracted to a magnetic field. So how can we predict if something is paramagnetic or not? And again, you have to write its electron configuration. Hydrogen. Hydrogen has one electron. If we're talking about an atom of hydrogen. It's a lowercase s. 1s1 would be its electron configuration. Now, you should be able to interpret this to tell you, hey, you know what, this is paramagnetic. The other way to represent electron configurations is using the box diagram. I draw the box diagram, but I don't actually draw the box. I just draw a line. If you really want to, you can complete the box. 1s1. So in the 1s orbital, we have one electron. How do we represent that? Well, use a different color. This is my electron. We represent it with the half arrow. Pointing up is referred to as spin up. Pointing down is spin down. If we only have one electron, by definition, it has to be paramagnetic. If we have an odd number of electrons, by definition, it's also going to be paramagnetic. Now, in the case of spin, I'm drawing this electron representing spin up, which is pointing up. Or it would be completely equivalent and acceptable to draw the electron with spin down. Both of these are going to be paramagnetic. Now, in the previous part of this video, I referred to the quantum numbers. You should be able to explain this or this in terms of the quantum numbers. Again, tying these representations together I'm going to leave that to you for now. So again, if you don't know what I'm talking about when I say spin up or spin down, go back and refresh your memory on your general chemistry, quantum mechanics. So, an atom of hydrogen, this is paramagnetic. Let's say we have helium. Let's say we have one atom of helium, and you might remember hydrogen in the atmosphere. In nature, it's found as a diatomic species. Helium is monoatomic, and we'll be able to really dive into the explanation of the noble gases and their chemical bonding later in the course. In other words, why it's monoatomic. What you learned in general chemistry is correct, but it doesn't give you all the answers to chemical bonding. So, going back to just an atom of helium, helium has 2 electrons. That gets us 1s2. Doesn't matter what the first electron goes in as, I'll draw it as spin up. The second electron must go in as spin down. There's no other possibility. Helium is diamagnetic. All of the electrons are paired. A diamagnetic species is slightly repelled by a magnetic field. Spin up, spin down. Why not have them both spin up or both spin down? That concept of spin, the best way to envision it is to think this electron behaves as the north pole of a compass. This electron behaves as a south pole of a compass, a magnetic field. North and south are attracted. If I put 2 magnetic north poles in this orbital, what would happen? Well, they would repel, right? So what we find is that spin is going to govern how we add electrons to atomic orbitals. The concept of spin, relating it back to something like I said, familiar like magnets, is very, very useful. There are many other layers to quantum mechanics that are beyond me. So if you watch some of the high-level physics videos where they talk about defining spin, you can start to melt down. So from a chemistry point of view, we're going to represent these with arrows going up and down and use again the concept of a north pole and a south pole. For our purposes, that will be sufficient. Diamagnetic versus paramagnetic. And there is a classical experiment, hopefully that was covered in your general chemistry class, where this phenomenon was discovered by passing hydrogen atoms and helium atoms through a magnetic field. The helium atoms went straight through, whereas the hydrogen atoms were strongly deflected one way or another because of this paramagnetism. If you have 1,000,000 hydrogen atoms, statistically, half of them will be spin up, the other half will be spin down. So the determination of spin up and spin down is random. It's flipping a coin. There's no energy difference between them. And that's what the magnetic field does of separating them into their respective spins. Helium, being diamagnetic, goes right through that magnetic field. It's slightly repulsed, but the way the experiment is set up, it's done in a way where it doesn't actually cause any perturbation. In other words, the atom doesn't move to the right or the left. So this again is another aspect of quantum mechanics that you should be very familiar with from your general chemistry. If not, go back, review this. This is directly tied to quantum numbers, to electron configurations. And as we get into the transition metals, for example, we're going to find that we have to write those electron configurations. We have to determine, are those species diamagnetic or paramagnetic? And it's more complicated in the sense that there are now d orbitals involved, but fundamentally nothing has changed because we're still using the quantum numbers and we're still using all of the same concepts that we've learned from general chemistry. So this is why I keep coming back to this idea of the foundational nature of quantum mechanics in Chemistry 111, your general chemistry class. You need to be eating, sleeping, drinking quantum mechanics before you step into my Chemistry 216 course because, said, once we get going, it's going to be more difficult to catch up. So in the next problem, number 3, I ask about writing ground state electron configurations. That should be self-evident. If you don't know how to do that, open up that textbook and figure it out. Because again, these are foundational. What I am going to do is work through a problem for number 4. Not one of the problems I gave you, I'm just going to make up another one. And with problem 4, I ask you to draw the Lewis dot structure, label any atoms with non-zero formal charges, state the electronic geometry, state the molecular geometry, what is the orbital hybridization of the central atom, and is the molecule polar or non-polar? So obviously quite a bit of information that I'm asking for any given molecule. Now, let's go with phosphorus pentachloride, PCl5, which is a main group element, and we'll talk about main group versus the transition metals versus the lanthanides later on. So PCl5, how do we draw a Lewis dot structure? Well, a big hint would be you need to have a periodic table in front of you, right? So the first thing we need to know, how many valence electrons does phosphorus have? And I'll pause for a moment. If you don't know what I'm talking about when I say valence electrons, again, that is another red flag where you might want to pause the video, go back to your notes, and then come back and look at this. Obviously, you can watch the video and get the answer, which is why this is not one of the problems from the quiz 0. There's no substitute for being familiar with the periodic table as you're trying to solve problems like this, Lewis dot structures. In other words, if you don't know the periodic table, you're going to be always a step or two behind. And I'll talk more about learning the periodic table as the course goes on. So, phosphorus has 5 valence electrons. Chlorine has 7 valence electrons, but there are 5 of them, right? So that's 35 valence electrons. This would be 5. So we sum these up, and we have a total of 40 electrons to work with for the chemical bonding. Again, these are the valence electrons, the electrons on the outer portion of the atom, if you will, the S and the P. So what's this going to look like? Well, when you're given a molecule, the first atom, by convention, is the central atom. There are some exceptions. For example, H2O for water. H2O, well, hydrogen is not the central atom. But in most cases, the central atom is first. If it's not, it's written in bold, or you're given some information. So this brings us to isomers. But in this case, that won't be a problem. So phosphorus is the central atom. Okay? So I put the phosphorus there. Now I'm just going to draw the chlorines. Like this. And I'm not trying to show a three-dimensional geometry. So my positioning of the chlorines is intentionally bad. Because the point I want to make is, when you draw a Lewis dot structure, that does not necessarily represent the three-dimensional structure of the molecule. A Lewis dot structure represents atomic connectivity and bond order. In other words, is the bond a single bond, a double bond, a triple bond? Lewis dot structures also will represent valence electrons that are non-bonding, the lone pair electrons. So as you are solving these problems, you need to be able to make the distinction between a Lewis dot structure and the electronic geometry and the molecular geometry. So that's one of the keys. How do we make this into a molecule? Well, first of all, something I didn't put into the question. These molecules are not ionic; they are covalent. In other words, if I gave you the structure of sodium chloride, or asked you for the structure of sodium chloride, that's going to be pretty easy. But in this case, we're talking about covalent bonding, right? So they're going to be sharing electrons. To make a molecule that has covalent bonding or polar covalent, I tried to merge those two words together, first thing we need to do is put a single bond in, right? So that's 2, 4, 6, 8, 10 electrons. Whether these chemical bonds right now are pure covalent or polar covalent doesn't matter. We need connectivity, so a single bond to everything. In some molecules, you might need to put a double bond or a triple bond. That's fine, but always just start off with single bonds and then work your way towards it. Again, that's the approach I've always taken. So 2, 4, 6, 8, 10 electrons. So we have 30 electrons to work with. Keeping track of the electrons is tedious, but it is absolutely vital. So you might think, oh, I can just do it in my head. And in many cases, once you've got experience, you can. However, if you make a mistake when you're counting your electrons, when you're keeping track of them, that will lead you down a very bad path, because you'll try and put in 48 electrons or 32 electrons or whatever, and the structure will fail. We start with 40 electrons. We must finish with 40 electrons. Okay? And from my experience, especially in general chemistry, over 95% of the mistakes in Lewis dot structures come from miscounting the electrons. Too few electrons or too many electrons. Something that should disturb you, what's that octet rule thing again, right? Octet, 8, right? 2, 4, 6, 8, 10. 10 is not 8. 8 is not 10. However, the octet rule is not etched in stone. Even if it was, it really wouldn't matter. The octet rule can be violated by heavier elements. The d orbitals can participate in chemical bonding. So again, this is something that hopefully was covered in your general chemistry class. If this does not sound familiar, we're going to go over it. But you should have, at the very, very, very least, been familiar with the octet rule. But there are exceptions to the octet rule. That is why Chemistry 216 and other courses exist, because Lewis dot structures are very useful, but they are fundamentally flawed. And sometimes they melt down, like this molecule. PCl5 is a perfectly fine chemical compound. You know, you can buy it, you can make it, but it violates the octet rule. So we have 30 electrons to go in here. Now, phosphorus is violating the octet rule. Chlorine does not necessarily have to violate the octet rule. So what I'm going to do is I'm going to give each of the terminal atoms an octet and go from there. So 2, 4, 6. Chlorine now has an octet. So that's 12, so 2, 4, 6, so that's 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. You don't have to count out loud as I'm doing, but it doesn't hurt. We just used 30 electrons. We have a grand total of 0 electrons left over. That is a very good sign. So all of our valence electrons have been accounted for, and phosphorus is violating the octet rule, but it's allowed to because it possesses d orbitals. Again, if you don't know how I'm justifying that, go back to your notes and your general chemistry textbook. Chlorine can violate the octet rule, but in this case it does not need to. So we have a chemical bond, 2 or 6 electrons in the lone pairs, so that gives us our octet. What about formal charges? What about the electronic structure? What about the molecular structure, hybridization, and so forth? So now that I've got you started on this problem, I want you to finish it. So I'm not going to answer the rest of these, at least not right now. And by the way, you don't have to finish working this particular problem. You can go ahead and work the rest of them that are on quiz 0. But this is really what I want you to get familiar with again, of writing Lewis structures, writing chemical formulas, writing electron configurations, because unless you've been taking a summer class, unless you do this for fun over the summer, you haven't done any of this in months. And it is something that if you've forgotten, again, how to navigate the periodic table, it will make your life more difficult as we go through the first few weeks of class.